On the off chance that you put it where the Sun is, it would expand to the orbit of Jupiter, a beast absolutely unsteady and on the verge of exploding. These are among the most conspicuous sources of radio energy in the entire universe, emitting more energy than a billion suns. Betelgeuse, or terrifyingly Bug Jew, is a red giant star. If you put it where the Sun is, it would reach out to the orbit of Jupiter. Immense, utterly unpredictable, and on the brink of detonation, this star has baffled astronomers for ages. When we think of stars, we typically imagine tiny twinkling dots in the night sky. Fundamentally, this is how they appear from Earth. But stars are far more than mere dots. They are enormous celestial phenomena. Betelgeuse, in particular, is vastly greater than our Sun. For many years, this star has puzzled researchers. However, recently, something particularly alarming has been happening with Betelgeuse, leaving scientists and other experts deeply concerned. Join us as we explore the astonishing new discoveries about Betelgeuse, its imminent destruction as predicted by the James Webb Space Telescope, and what these revelations could mean for our universe and life on Earth. As physicist Michio Kaku explains, Betelgeuse is a colossal wonder, an enormous star that has fascinated astronomers for so long. A Greek astronomer named Antonius was among the first to document it. This star is so massive that it can be seen in the night sky from Earth, particularly during winter. If you're into astronomy, you've likely heard of this star. The reddish-orange star marks the upper left shoulder of the Orion constellation. Despite being one of the brightest stars in the night sky, Betelgeuse's brightness isn't constant. It fluctuates. This variability is one of the star's remarkable features, but it isn't the only one. Let's delve into some of Betelgeuse's specific characteristics. Most stars in the night sky are incredibly distant. The nearest star is 4.2 light-years from Earth. To grasp the concept of light-years as a measure of distance, imagine traveling at the speed of light for an entire year. Light travels at 186,000 miles per second. Thus, in a year it covers an astonishing distance, equivalent to 1 light-year. Doing the math, 1 light-year amounts to billions of miles. When we say the nearest star is 4.2 light-years away, we mean it's billions of miles from Earth. Now, consider this. Some stars are much farther away, and Betelgeuse is one of them. Betelgeuse is approximately 600 light-years from Earth. Even if we could travel at the speed of light, it would still take 600 years to reach it. Since we cannot travel that fast, not even our fastest rockets can, Betelgeuse's visibility is all the more remarkable. If you're wondering how Betelgeuse can be so bright despite its distance, the answer lies in its extraordinary characteristics, such as its size and luminosity. Betelgeuse is about 1,000 times larger than our Sun. Its radius is estimated to be numerous times that of the Sun, making it appear as a disk in space through modern telescopes, while other stars appear as mere points of light. This phenomenon is attributed to the reactions occurring on its outer atmospheric layer. In terms of mass, Betelgeuse weighs around 12 to 19 solar masses. A solar mass is the standard unit of mass used by astronomers, equivalent to kilograms. However, scientists cannot determine Betelgeuse's exact mass since there are no planetary bodies orbiting it for comparison, and direct measurement from Earth is impossible. Nevertheless, this makes Betelgeuse many times heavier than our Sun. Betelgeuse's brightness ranges from a magnitude of +0 to +1.6. In simpler terms, Betelgeuse is significantly brighter than our Sun. It's no surprise it's nicknamed a red giant. However, Betelgeuse's brightness doesn't remain constant. It oscillates. This variation is due to its pulsations. Betelgeuse expands and contracts. When it expands, it becomes brighter. When it contracts, it dims. This cycle can last from 10 to 100 days or even longer. A unique property of Betelgeuse is its surface, which is covered in dark magnetic spots. The magnetic field in these spots is much stronger than on the average surface. Unfortunately, these magnetic spots obstruct the flow of hot gas to the star's outer layers, causing cooler regions. Betelgeuse has many more of these spots compared to our Sun, which explains why it is cooler despite its immense size and brightness. The Sun also has dark magnetic spots, but those on Betelgeuse are much larger and significantly more numerous. To illustrate, some of Betelgeuse's spots can be twice as large as Earth. Betelgeuse also boasts a magnetic field that is several times stronger than the Sun's. This strong field causes the gases on its outer layer to appear as loops or arcs when observed through a telescope. Betelgeuse has a surface temperature of about 3,500 Kelvin. This low temperature contributes to its low energy emission and its dim red color. Although Betelgeuse is red today, it wasn't always so. Approximately 1 million years ago, it was yellowish, similar to our Sun. Over time, its color shifted to orange-red, and about 40,000 years ago, it became the red star we recognize today. This color change indicates to scientists that Betelgeuse is evolving. It emits about 100,000 times more energy than the Sun. If it were closer to Earth, it could have rivaled the Sun as our primary source of light and energy. The fact that a star 600 light-years away can still be seen with the naked eye at night is extraordinary. Our Sun is just 8.3 light-minutes away from Earth, which is why it appears so bright. If Betelgeuse were as close as the Sun, it would engulf Earth and the inner planets due to its colossal size. Even if it matched the Sun in size, it would still emit far more radiation. Betelgeuse, also known as Bug Jew, is a massive star located in the Orion constellation, around 600 light-years from Earth. Its enormous size and brightness make it one of the most fascinating celestial objects in the universe. On numerous occasions, more prominent than our Sun concerning sweep and size, Bug Juice could undoubtedly incorporate the orbit of Jupiter if placed at the center of our solar system. This incredible size allows Bug Juice to appear as a disk rather than a point of light when observed through powerful telescopes, unlike most other stars. Despite its tremendous size, Bug Juice is not the most massive star. Its mass ranges from around 12 to 20 times that of the Sun. This variation in mass estimates arises from the challenges in precisely measuring the mass of stars lacking companion stars or other objects to provide gravitational reference points. Even at its lower estimated mass, Bug Juice remains a colossal celestial body. The brightness of Bug Juice is another key characteristic. It fluctuates consistently over time, with its brightness ranging from magnitude 0 to plus 1.6. For comparison, a magnitude 0 star is about 2.5 times brighter than a magnitude plus 1 star. At its brightest, Bug Juice can ultimately shine up to 100,000 times brighter than our Sun. This variation is attributed to its pulsations, irregular expansions and contractions caused by internal cycles within the star. When Bug Juice expands, it becomes brighter. When it contracts, it dims. These pulsations can last for years, contributing to its dynamic appearance in the night sky. Bug Juice's surface temperature is relatively low for such a massive star, measuring around 3,500 Kelvin. This gives it a distinct red hue, typical of red giant stars nearing the end of their life cycles. Like other red giants, Bug Juice is in the late stages of stellar evolution. It has exhausted the hydrogen fuel in its core and has begun fusing heavier elements. This fusion process generates energy and causes the star to expand outward. The star's atmosphere is rich in complex physical phenomena, displaying dark magnetic spots on its surface where the magnetic field is stronger than in surrounding areas. These spots inhibit the convection of heat, leading to cooler regions on its surface. Despite these cooler spots, Bug Juice remains a massive, energetic star. However, it will eventually meet its end in a spectacular supernova. Bug Juice is a massive star nearing the end of its life, and its ultimate fate will be dramatic. Once it runs out of fuel, it will undergo an intense fusion process, forming heavier elements like helium and carbon. This will cause the star to expand to even greater sizes, possibly becoming one of the largest stars visible in the night sky before it dies in a cosmic explosion. The supernova's impact will be powerful enough to temporarily outshine an entire galaxy. This event will likely send shockwaves through space, and Bug Juice could potentially do just that. However, such an occurrence is not expected to happen soon. Scientists are still uncertain of the exact timing of Bug Juice's end. Advanced instruments like the James Webb Space Telescope bring us closer to understanding when this might occur and how its death will shape the universe. Bug juice, also known as Betelgeuse, is a fascinating example of a massive star approaching the end of its life cycle. It provides astronomers with a captivating window into the life and death of stars. Part of the Orion constellation, it is one of the most studied stars in the night sky. Its enormous size and brightness make it an important subject for understanding stellar evolution. As bug juice approaches its end, it undergoes extreme changes, offering insight into the fate of massive stars and even the evolution of galaxies. One of its most captivating traits is that it is a variable star. Specifically, bug juice is a semi-regular variable star, meaning its brightness fluctuates irregularly over time. These variations, visually striking, provide valuable data about the star's internal structure and processes. As it expands and contracts, bug juice sheds layers of its outer atmosphere, contributing to its variability. These pulsations are believed to be linked to complex nuclear processes occurring in its core as it depletes its hydrogen fuel. When bug juice expands, its surface cools, taking on a redder hue typical of a red giant. The cooler temperatures of red giants are associated with the late stages of stellar evolution, when a star has consumed much of its hydrogen fuel and begins fusing heavier elements like helium and carbon in its core. This process causes the star to grow larger. Bug juice has expanded so much that if placed at the center of our solar system, it would extend beyond the orbit of Mars, engulfing the inner planets, including Earth. However, it is important to note that bug juice is still in the relatively early stages of this phase, and its eventual death will be far more dramatic. One of the most intriguing aspects of bug juice's behavior is its unpredictable pulsations. These pulsations affect not only its size but also its luminosity, leading to significant changes in brightness. Scientists study these fluctuations to better understand the internal processes occurring within the star. In addition to its pulsations, bug juice is surrounded by a dense cloud of gas and dust. This cloud contributes to its occasional dimming, as the material blocks some of the light escaping into space. The cloud is a byproduct of the star's significant mass loss during its later evolutionary stages. Ultimately, bug juice will lose enough mass to trigger a catastrophic gravitational collapse, leading to a supernova explosion. This event will produce a neutron star or possibly a black hole, depending on the star's final mass. Bug juice's supernova will be an event of immense scientific interest. When it occurs, the explosion will release vast amounts of energy, briefly outshining the entire galaxy. Although bug juice is about 600 light-years away, the explosion could still impact its surrounding environment, such as triggering the formation of new stars in nearby gas clouds. The core collapse of bug juice will leave behind a fascinating remnant that will continue to influence the universe long after its death. While the star is still far from reaching this final stage, its eventual demise is one of the most anticipated astronomical events. Observations from advanced telescopes like Hubble and the James Webb Space Telescope continue to refine our understanding of its behavior and stellar evolution as a whole. Bug juice serves as a reminder of the immense power and complexity of stars. These celestial bodies are dynamic, undergoing changes that impact their systems and the surrounding space. As scientists monitor bug juice's behavior, they gain insight into the mechanics of stellar death, black hole formation, and the cosmic recycling process that occurs when a star dies. Ultimately, the legacy of bug juice will live on, not just in its supernova explosion but also in the ongoing study of stellar evolution and the forces shaping the universe.